And hello everybody, welcome back. We're going to continue our discussion on K Omega SST. So in the last video we was over here trying to get this bottom term to be dimensionless so that we can start plotting using the functions that we know. And yeah, what I want to kind of focus on is this. Well, there seems to be this extra density term over here, which seems kind of odd because this makes the term at the bottom here in units of density, and this is kind of funny because this should be dimensionless if this outside is supposed to be dimensionless, this term inside is supposed to be dimensionless. If not, the units don't match and there is something pretty off with this function. So I did a quick check over here. It's based on the actual literature. It says some improvements to Menter's K Omega SST turbulence model. This paper specifically deals with surface roughness, okay, and how it affects the wall functions in the K Omega SST turbulence model. And what I found out was that this gamma, which is the so-called function, the function for which is f1. Yes, this is the argument inside, which is this min max thingy inside. All right. In this paper, there seems to be a density on top of this K Omega SST, the function. So I'd like to just copy and paste this. This is the blending function. All right, and okay, I want to do the non-dimensionalization. So I say, hang on, why is there an extra density term in the denominator? So yeah, it looks like there is a typo. So I'll just get the citation here, APA version. Okay, looks like there. Okay, wait. Control, and I'll just paste the text. This is from this paper. You can find it on cfd.mac.manchester.ac.uk. This one is a free, I think. Okay, so an earlier paper, and there is a density term in the numerator. Okay, so it looks like this one is a little off. I think there was a mistype of a density here. Okay, I don't know if the OpenFOAM code has the same thing, same issue, but hopefully it does not. Hopefully a lot of the CFD codes they do take this into account, because this doesn't seem to have a density in the numerator, so it does look kind of iffy to me anyhow. And it's the same whether you look at this website or some other websites with the K Omega SST model. There's a row missing in this numerator here, so that should be in the numerator. If not, the dimensions are a little off. So okay, now we kind of figure that out. Then let's do this. Yeah, let's do this. We can take a look at this term again. Okay, this one I can just kind of delete later. Okay, so let's correct this. Yeah, so this is supposed to have a density term in the numerator. Okay, so the density term is supposed to be here. And yeah. Okay, so we want to kind of figure out what is this term over here. And because this term also happens to make itself visible in the denominator. Okay, it should be here. So I will get this. Now put this here. Okay, so it looks like this rho u star nu squared. This term is quite important. Alright, so this one I will just change it to a neater looking version, which is this. Yeah, so we need to just look at this. Now, of course, this one, this is an approximation in the boundary layer. May or may not be correct, but it's just here to give us an idea of how this thing actually varies with y plus. Okay. So in actual fact, this may be a little bit more, but okay, never mind. Back to this. We want to find this, and we know that u star, okay, u star equals to square root tau wall over rho. Alright, so we can just substitute that in there, and we'll get tau wall over rho squared. Okay, so we'll just get tau wall over rho squared, and then we will have this tau wall squared over rho nu squared. Alright, so that's what we are having here. Okay, and or rather we can just have this instead, rho squared nu squared. No, I'll just do that. Okay, so this tau wall equals to tau equals to rho nu plus nu t u dy. This is at the wall. Okay, so this is tau wall. Alright, at the wall, nu t equals to 0. So we'll have that. Alright, and du dy. So we can non-dimensionalize that as well. So du dy. Okay, let's get y in terms of y plus. Okay, we'll have this here. Y equals y plus, and u equals u plus u star. Okay, and okay, this should not be here. Yeah. So anyway, back to the point. Yeah, we can non-dimensionalize as follows. We just do this and do this. All right, and we just get nu out here. All right, y plus. I hope I'm doing it right, but okay. So this nu plus will go. This nu will go, and then you'll have a u squared here. Okay, so that okay, in the VSL region, viscous sublayer region, du plus dy plus equals to 1. Okay, so we'll just get tau wall equals to rho u squared. Okay, that's how we get it. And we'll just get this over here. Okay. Okay, anyway, okay, I just quickly substitute like so. Looks like it gets us back in square one, so that's not the right way. Yeah, so how do we go from here? Okay, so let's go back to our equations here. And I'll copy and paste this over here. And looks like we can't cancel out all the terms here. Okay, so there's it is not a dimensionless number. This is not a dimensionless number, but let's see what we can do. So I'm going to copy and paste this term here. I'm going to paste this term at the bottom, and I'm going to bring this term out. Okay, and inside will be just nu square divided by rho u star to the 4th. Alright, so that's the friction velocity. This part and this part will cancel. This, or I can shift it to the top. And that's it. Now we have some function. In terms of this, dimensionless quantities. And it appears that this term over this term is overall dimensionless. It seems that this 10 to the power of minus 10 is not a dimensionless number. It has some dimension to it as well in terms of this. So what is this max at the bottom thing look like? Well, I can't say too much yet, but what it looks like is that, okay, you have some fixed number that is dependent on the kinematic viscosity and the friction velocity and the density. Okay, so this is some fixed number, and this is a function of rho, okay, rho u star 4th over nu squared, right? This is some function of that. And okay, this part which I'm highlighting here, that is dimensionless. So that's only a function of y squared, right? So you have this part, some function, and this one is a function of y plus. This is a function of y plus. Alright, so I'm just giving you an arbitrary curve, and what the maximum thing does is that it sets a floor for how low this thing can go. So I'm going to highlight that part, and I say, okay, over here and over here is where, you know, this part you kind of don't consider because that's too low. So this thing kind of sets a floor based on the properties of the fluid and of course the friction as well, the shear stress. Okay, so not easy to give you a set number that's universal throughout all fluids, but what we can do is a parametric analysis. We can do parametric analysis to see the effect of the value of this. Okay, so let's say for water it will be different, for air it will be different, of course, because nu and rho will change, and of course the shear stress will change as a function of a Reynolds number. So this last term is really a function of a Reynolds number, alright, of the flow, right? Because if you remember the friction factor in pipes, that's always a function of Reynolds number and roughness, right? Roughness. Okay. surface roughness. All right, and what I was sharing with you before was that this okay, not this paper. Was it this paper? No, not this one. Yeah, it's this paper. Yeah, it says that yeah, this paper, it says that this is there are surface roughness functions for this K Omega SST model. Okay, it's found in section 2.2, and then you see KS plus popping up again. I'm not going to go there now. I just want to quickly finish this so that you can see at least a trend. So what I can do is I can show you various values of this and see how that will affect these values. I mean the CDKW, right? And ultimately this value here, because this value will be dependent on the density, kinematic viscosity, and of course the wall shear stress or the friction velocity. So I can just give you a rough idea of different orders of magnitude of this, and you'll see what happens. All right. Okay, so the first thing I want to do is to get this top and bottom in terms of y plus. Okay, or at least the bottom part in terms of y plus. All right. So this one at the top is already pretty simple, because k plus we have a what do you call it? We have a very simple function for it already. We have it in our Excel. Okay, so where is it? Okay, up. So k plus we already have in Excel plotted. Okay, so next thing is this d omega plus dy, d omega star plus dy plus. This will be equals to yeah, where is it? Yeah, this is where we are. Okay, so depending on the form, omega plus can be as follows, and the differentiating of that will also take different forms. So yeah, where we go down, yeah. So okay, we can just do simple differentiation, and in the viscous sub layer, we will get we'll bring this down. Okay. K6 over beta 1 y plus close bracket q. Okay, so you have minus 12 here. Alright, so I will give so row below and just do a differentiation to get that. And then this one I'm just going to ignore. Over here it's just you will see the square come out, 1 over y square. Okay, so alright, so this one I will just get to -1, and you have a y square at the bottom, and that's it. Okay, it kind of decreases with increasing y. Okay, this, however, dk plus dy plus, that's even simpler, because if you know, it would kind of just reduce to 0. You see, It just reduces to 0. So that saves us a lot of effort here. Okay, for k plus, or for this, it is equal to 0 in the boundary layer. So effectively, this term can almost become negligible in value, can become 0. Of course, we made the approximation that we made the approximation that this, I mean the other two terms don't matter in the x and z direction, but apparently maybe they do matter. Nevertheless, the contribution may be pretty small. Anyhow, so it looks like the number is being set by this floor, which is 10 to the power minus 10. Okay, 10 to the power of minus 10. So we don't really have to do any kind of calculation there. Okay. Okay, in the boundary layer, this one may be gone, so I will just the first term may be negligible. Now, this is an approximation. Just be mindful of that. I'll just have this at the bottom and this at the top, and the k plus in the boundary layer is 0. Okay. Okay. Wait. 0 in the viscous sublayer. 1 over 0.09 in the turbulent sublayer. Okay. Okay, so this equals to 0 in viscous sublayer, and this one will be equals to some finite value, 1 over c mu. Okay, c mu in the turbulent sublayer. It'll be slightly different. Okay, so either way, because this thing kind of reduces to 0, we are left with a good estimate for this term to be this much. So what is this term? It looks like a 1 over y squared varying term. Okay, so sigma omega 2, where is it? Hopefully they didn't copy it wrong this time. Sigma omega 2, it's here, 0.856. Okay, so this is just an estimate again. Square root c mu equals to square root 0.09, and that's equals to 0.3. Okay, so that's simple, 0.3. And what else? Okay, 4 times 0.856 over that. Okay, divide by 10 to the minus 10. So that's going to be a very big number. Okay, so this over 10 to the minus 10. Okay, I'm just going to calculate that. So equals to 4 times 0.856 divided by 0.3 divided by 1e minus 10. Alright, so it's going to be a horribly big number over there. Okay, so that will vary with 1 over y plus in the viscous sublayer. Okay, so overall, okay, I can approximate this as such. this big number here over this term, and then you'll have y plus squared. Okay, so that's not too bad. We can plot that out easily. So I'm just going to copy that here. So 0.03. Okay, constant. Okay. And yeah, constant, and you divide it by y square. So copy and paste this here. I want to have three functions. So I have this let me just call this thing big Z. Yeah, let's call this thing big Z, because I just don't know. I'm running out of names to put it, to give it. So this is Z. Alright, now insert a few rows above and there. Okay, so Z, where new square. Alright, okay, and I think I want to give that term a new a new name. So that is, I will put maybe zeta. Okay, I'll put zeta. The term hasn't been used, but I'll just put it like that. Put it in Excel. Put it in Excel as such, and zeta equals to 1. Okay, 2 orders of magnitude less becomes zeta equals 0.01, and 2 orders of magnitude more, zeta equals to 100. Okay, so that's where we get it. Alright, so we can see 3 different orders of magnitude what this function will look like. Okay, so zeta equals 1, so it goes to this constant, and then I'll log this. Okay, I'll log this, and I'll divide it by 1 times y square, y plus squared. Then I'll go all the way down. Okay, this one is, okay, I want to lock the cell as locking the U. Okay, then I'll just put the 0.01 here, and last one here I want to put 100. Alright, so looks like this zeta equals 1 kind of yeah, it's a very large number. So in the boundary layer, we kind of don't consider that value. Okay, let's see the series. My goodness. So regardless, anyway, this function is so big that in the boundary layer it is several orders of magnitude over these two functions. Okay, yeah. So okay, that's what the z function looks like. What this looks like in a boundary layer. So next video these are just estimates, all right. Yeah, but next video you can look more into how these affect the final, F1 function, right? Okay, so thanks for watching. I'll see you guys next time. Bye bye.